Hi students, in last video we have seen the Raoult's law and ideal and non-ideal solutions, distinguish or difference between ideal and non-ideal solutions. Now in this lecture we are going to see the vapor pressure of ideal solution of miscible liquids. Now we know what is ideal solution. Ideal solution which obey Raoult's law at all temperature concentration condition. That means this solution obey this equation Pa is equal to P0A XA, Pb is equal to P0B XB. Now if we want to draw the vapor pressure curves of these ideal solutions of miscible liquids, then first of all we have to consider the liquids, that is pure liquid A, pure liquid B, pure liquid A, pure liquid B. Now here vapors of A and vapor pressure of that pure A is P0A and that of pure B is P0B. And if we mix these two together, then this vapor pressure is the total vapor pressure of solution. Now if you want to draw the curve, vapor pressure curve versus composition, then you will get the vapor pressure composition diagram of ideal solutions of miscible liquids. Now consider here pure A and pure B. That means here mole fraction of A is equal to 1 and here mole fraction of A is equal to 0. That means mole fraction of B is equal to 1 and here mole fraction of B is equal to 0. Now if you consider pure component A and if we measure the vapor pressure of this pure component A, now suppose this is the point, that is P0A is the vapor pressure of pure component A, and if you consider pure B here, that means XB is equal to 1, then if suppose the vapor pressure of that pure B is P0B. Now according to equation, that is Raoult's law equation, PA is equal to P0A XA and PB is equal to P0B XB. Now these equations shows that if we draw PA versus XA or PB versus XB, the straight lines should be obtained. Now how these straight lines obtained, let us see. Now suppose if we have any composition of this, suppose that composition is, this composition is 0.9A, XA is equal to 0.9 and XB is equal to 0.1. That means this composition here. And if you measure the vapor pressure of this solution, that means partial vapor pressure of this solution. If you measure partial vapor pressure of this solution, because now this is contaminated with B, and therefore it is not pure vapor pressure of pure component. It is contaminated with B, and therefore here we measure or here we calculate the vapor pressure of A component in that particular solution. That is a partial vapor pressure of A. Partial vapor pressure of A. Now, if we determine partial vapor pressure of A using this Raoult's law, now that vapor pressure decreases. That vapor pressure decreases. This is the vapor pressure of A component in solution. If you consider another composition here 0.8, 0.2, then vapor pressure becomes this, and if we perform the experiment, then here we get the, and if we join this, we get a dotted line, dotted straight line, and equation of that is PA is equal to P0A XA, because with the help of this equation we determine the vapor pressure of A component in solution. That means partial vapor pressure of A component. Now it is somewhat curved, it should be straight line, and therefore if we join these dots, here we get this straight line. We show the partial vapor pressure of A component. Now if you consider this pure B, the vapor pressure of pure B is P0B, and if we add A component, then that composition will be, suppose 0.1 is the mole fraction of A in that particular solution, then the mole fraction of B will be 0.9, and therefore this will be the composition on this composition axis. And if we determine the partial pressure of B with the help of this Raoult's law equation, then it comes to be here. That means the vapor pressure of A in solution decreases on addition of another component, and therefore if we go on adding B, if we go on adding A in this particular solution, then composition of A increases and composition of B decreases, and therefore we will come across this dotted line. That means if we connect these lines, then here we get this curve, and this curve represents the partial pressure of B, and that can be calculated by using equation P0B into XB. P0B into XB. These are the two dotted straight lines which represent the partial vapor pressures of A and B respectively. And these are straight lines according to these equations. If we plot partial pressure of A versus mole fraction XA, and if we plot partial vapor pressure B versus mole fraction XB, then here we get two straight lines. Now if we consider any composition here, and if we add on these two vapor pressures, that means this is PB and this is PA, and if we add these two, here we get the total vapor pressure. That means what? According to this equation, P is equal to PA plus PB. That means at this particular composition, the vapor pressure of B becomes PB and vapor pressure of A becomes PA. And therefore, if we add these two according to Dalton's law, the vapor pressure, total vapor pressure becomes this. For this composition, that becomes this, and therefore, if we connect these points, here we get the straight line which represent the total vapor pressure line. Total vapor pressure line, which will be obtained by adding partial vapor pressures of A and B. And this is the vapor pressure diagram for ideal solution of miscible liquids. Now these are the straight lines. Now next, further we are going to see the vapor pressure of non-ideal solutions, of miscible liquids. As we know, solutions which do not obey Raoult's law at all temperature concentration conditions are called non-ideal solution. That means they deviate from ideal behavior. These solutions deviate from ideal behavior. And therefore, according to nature of deviation, non-ideal solutions are classified into three types. And which are these types? Let us see. Now here, deviation from ideal behavior is somewhat different in different types. First is the total vapor pressure lies in between the vapor pressure of pure component. This is type 1. We show small deviation in total vapor pressure and also partial vapor pressures of the component. Second type of real solution, that is non-ideal solution, is the total vapor pressure rises to maximum and show positive deviation, large positive deviation, and this total vapor pressure is well above the vapor pressures of the either of the component. And third type, total vapor pressure decreases to minimum and this minimum is well below the vapor pressures of the either of the components. Now let us see vapor pressure curves, how the non-ideal solution behave in these different types. Now let us see type 1. Type 1, here total vapor pressure lies in between the vapor pressures of pure component. That is small deviation from ideal behavior. Small deviation from ideal behavior. Now, as usual, the diagram for that is now for ideal case. This is the diagram. Dotted lines represent the ideal behavior. A, B, P0A, P0B. Now in type 1, there is small deviation in the total vapor pressure as well as the partial vapor pressure. This continuous line represents the behavior of non-ideal solutions. Small positive deviation. Now this is small positive deviation. Now here total vapor pressure lies in between the vapor pressures of pure component. No any composition has the vapor pressure above the vapor pressures of these two limits. They are limit between these two, this vapor pressure lies. And here also same. Here also the same. The small deviation takes place. For example, here we have benzene toluene system. Benzene toluene mixture acts as a type 1 mixture, that is non-ideal system. It has small deviation. Now let us see type 2. Type 2, total vapor pressure rises rises to maximum, and this maximum is well above the vapor pressures of pure components. That means system with large positive deviation. Large positive deviation. Now this is type 1. Now type 2. Again consider the diagram A, B. This is ideal situation. Dotted line represent ideal behavior. Now in this type 2, the total vapor pressure rises, attain maximum, and therefore this maximum is well above the vapor pressure of either of the component. It is well above P0A and also that of P0B. The partial vapor pressure also has large positive deviation. The continuous line represent this particular behavior of non-ideal solution of type 2. Now example is propyl alcohol and water. Water and propyl alcohol. Water and propyl alcohol. The type 3, total vapor pressure decreases to minimum, and this minimum is well below the vapor pressure of pure component. That means the system with large negative deviation, and this can be represented with the help of diagram. This is ideal situation, ideal behavior, A, B, P0A, P0B. Now here in this case the total vapor pressure decreases, attain minimum. That means this minimum is well below the vapor pressure of either of the component. That means this minimum is well below this P0A and also of that P0B. And partial vapor pressure also show large negative deviation, and this is the behavior of non-ideal solution of type 3. The continuous line represents the non-ideal behavior of total pressure and partial pressures. Now this behavior exhibit the water sulfuric acid system. Now this is all about the vapor pressure of non-ideal solution or behavior of non-ideal solution of these 3 types. This is all about this particular unit. In next video we will see the vapor pressure boiling point diagram and further. Thank you. रुको